Deputy Dean of the Penn Engineering. Before that, he was the director of the Grass Lab. Many of us have collaborated with folks at Penn before, including Grass Lab. But other than just doing outstanding and incredibly great research, he also managed during his spare time. He was the Deputy Dean of Research for 4 years, Department Chair for Mechanical Engineering for 4 years, and the Deputy Dean for Education for another 4 years. And then he had managed to spend some time in the White House advising the science and technology as well. So it's really, really incredible journey that he has been taking. Vijay is also a fellow of ASME, that's American Society of Mechanical Engineers, as well as a fellow of IEEE, and he's a member of National Academy of Engineering. Needless to say, he also has received many, many Best Paper awards. Too many, I cannot list them all. So I'm going to end right here and hand over the floor to him, and let him tell us some of his most recent work on aerial robot swarm. Go ahead, Vijay.
Thank you. Thanks very much. Actually, I was trying to remember the first time I met you, and I think at that time you were a program officer at ARO, and I got one of my first grants from you, so thanks very much for getting me started. It's really a delight to be here. I've really enjoyed my day here. A lot of interesting work going on, and I thank you for the opportunity to share some of the work that we're doing in aerial robotics. Before I get started off, so I became the dean 3 months ago, roughly 3 months ago, and according to the new dean, everybody should have this first slide on their presentation. So this is a picture of our new nanotech building, and I thought I would present this to give you some sense of the composition of Penn Engineering. It is the first engineering school established in the first university, which is due to Ben Franklin in 1749. And if you could look at this rough faculty of 116, about 14 practice professors, research professors, and full-time lecturers. The computer science department is about 30 faculty, and it's roughly the same size as UNC. The great thing is that we're planning to grow by about 33% in the next 5 years. So for those of you looking for academic positions, it's a great place to apply to. And also, it's right in the middle of the city, just a very rich and vibrant campus, and I'd love to tell you more if you're interested. But what I'm really here for is not to sell Penn, but instead talk about my own work, which is on aerial robot swarms. And I thought I would start by showing you a picture of our aerial robots. And I hope nobody here is from the FAA. If you are, I'll tell you that this picture was shot in South America. If not, this is the Penn campus. This is the other side of the Penn campus. And I'll tell you a little bit about our work. But first, I want to just give you a quick overview of the industry that is associated with aerial robots or UAVs, and then tell you about how we think about controlling these UAVs. It is a model-based approach, and I want to tell you a little bit about this because not only do we design software, but also the electromechanical system that comprises the platform. And then tell you about one of the big challenges we have at designing good systems at this level of state estimation, which is the problem of determining what the position is, what the velocity is of the UAV. And then cooperative control, how we get multiple vehicles to collaborate, and then tell you some of the applications we're trying to address. So spending roughly 10 minutes on each idea. So first, with the UAV industry, and before I get started with that, I should tell you that we have sponsorship from many federal agencies along with industry partners, and I'm required by my lawyers to declare to you conflicts of interest lest I promote ideas from our spin-off companies. So KML Robotics was recently acquired by Qualcomm, so I don't have a conflict there. Nauka Technologies is a company we started looking at farming applications. Identified Technologies is a spin-off in Pittsburgh looking at aerial mapping. Exyn Technologies is a company that looks at security and disaster response type applications. And then finally, flown. I'll tell you a little bit about this, which is really on the more personal, intelligent, and social robot side of things. Back to the question of unmanned aerial vehicles. So this is a slide that I showed in 2010. Things were taking off dramatically. You could see that 1980 there were hardly any UAVs. And the thing that made this, and by the way, this is on a log scale, so this exponential growth was possible primarily because of the growth of GPS-like sensors, IMU-like sensors, and really processors in general. So at that time, there were predictions of a $10 billion industry with lots of interesting military applications, civilian applications, primarily driven by the DIY drones organization. So if you go to DIYdrones.org, started by Chris Anderson, who was then with Wired magazine, he started this, and it attracted about 1 million or so developers by the time in 2010. And the FAA boldly predicted that this industry is going to take off. We're going to have 15,000 civilian drones by 2020. So, and by the way, we started working with these kinds of geometries, these quadrotor geometries, back in 2006, long before they became popular. But before that, much of this work was really in fixed-wing aircrafts. So this is in 2010. You fast forward in 2015, and of course, things have really just gone crazy, right? There's a lot of popular press about this. Everybody is talking about drones. They said 15,000 by 2020. Well, 15,000 drones are sold just in the US every month. And this year in Christmas, they expect to send 1 million drones just this December worldwide. So this has really become a huge industry. And now it's a $15 billion industry. Now they say it's going to grow to $25 billion by 2020. And you know that this prediction is also going to be off. But the thing that's impressive now is really just the broad industry that's being impacted by this: agriculture, inspection, patrol, security, photography, virtual tourism, movies. Okay. So things are exploding, as you can see. And it's not just these kinds of multi-rotor aircrafts. If you look at unmanned vehicles, broadly speaking, so we call these aerial robots, and of course the industry calls these drones, but it also includes, now these are military vehicles. In the Army, the military calls them remotely piloted vehicles, RPVs. But they're all part of the same family. So there's a lot of growth in the small vehicles, the research platforms, the commercial vehicles, and also these much larger vehicles. So I like to joke that if you look at the evolution of these platforms, we're actually just starting off. So there's a long ways to go, and just a lot of interesting stuff going on. So you can ask, why did all of this really take off? And of course, it goes all back to Moore's law. It started the semiconductor industry, the price-performance ratio of lots of things connected with computing falling. And today people will tell you that Moore's law is actually coming to an end. This is Moore's curse. People argue the Moore's party is over, and maybe things are slowing down. But I think that there's an after party. So this after party has to do with continuing trends. So there's a bunch of things you can look at. Computing costs going down roughly 30% a year. Same thing with storage. Same thing with communication. So if you can compute quickly, you can store data, and you can communicate. And there's one other thing that I don't have, which is really the sensor story. And the sensor story, the price has not decreased 30% a year, but it's getting there. With cameras, certainly it's gotten there, and more than that. But with the sensors we need for aerial vehicles, it's probably not at the same rate. But still, it's dropping dramatically. So this is one side of the story. I think the second side of the story is that the entry barrier is dropping. So for instance, today, my students are able to do electromechanical design in a matter of a couple of hours. You know, they come up with these modular designs of where to put microcontrollers, how to do power management, how to do processors, where to put the sensors, and these smartphone-like designs. And I call this a smartphone because it's roughly the same aspect ratio, roughly the same weight. you can put together relatively quickly. And if you have a fab shop, you can put these and manufacture them the same way you would manufacture smartphones today. So the barrier to entry to this field is dropping dramatically. And only last Friday, the FAA came up with these rules saying that now anybody who owns drones will have to have them registered. I mean, we have literally hundreds of these in our lab, and I'm just trying to think of how we're going to line up to register these with the FAA. It makes no sense. But the point is that the barrier to make these is actually dropping dramatically. It's not like you have to buy them. So that's the UAV industry. What I'd like to tell you a little bit about is not on how we build these, but instead on the software that sits on top of these platforms, which is where the value added really is. So let me tell you a little bit about why it's hard to control these if you want to do aggressive maneuvering, high precision maneuvering, and then tell you how we solve this problem. So most of our approaches are based on models, and then a little bit of learning that goes to wrap around the models to account for uncertainty. So at a very basic level, you're trying to control a 4-rotor platform, and you want to control position and orientation, which means you're really looking at both the 3 variables that describe the spatial position and the 3 variables that describe the orientation. Of course, you can use quaternions. In fact, we use rotation matrices. But essentially, you're controlling 6 things. And the big challenge is you only have 4 inputs. So the system fundamentally is underactuated. So that's really our first challenge. But fortunately, there's some attractive properties to the geometry and to the dynamics. So this property is called differential flatness. And because of this, while you might want to control these 12 state variables, 6 positions and orientations and their derivatives, and that sits on a manifold that's curved and ugly, it turns out that because of the properties of the system, you can actually describe it on a simpler submanifold, which is just the position and the yaw angle. And this manifold is actually almost flat. It's flat if you consider the Euclidean space XYZ. If you take the yaw angle and if you pretend that the yaw angle is not 360 degrees, but instead it goes from 0 to 359.9, then you can flatten it out, and that's this flat space. So it turns out that every trajectory that you can think of that sits on this complicated manifold and satisfies the laws of dynamics, that trajectory can be modeled by a sufficiently smooth trajectory on the left-hand side, which means the problem of planning dynamically feasible trajectories reduces to a problem of computational geometry. Find something that's sufficiently smooth, and you're guaranteed you should be able to follow it. So that's one simplification. So if I want to go from A to B in this more complex space, all I have to do is find the corresponding points on the left side and then plan the smooth trajectory on the left side. So our planning problem really is to find time parameterized trajectories in position Cartesian product with the yaw angle, which is SO2. Once you have that, we can think about control. And the big challenge in control is that the system is underactuated. I have a few equations here, but you could ignore those equations because basically what I'm describing is the simplest form of control, which is proportional control and derivative control, as I'll explain in a minute. So the idea is you're given a trajectory and you want to follow it. So a standard way of doing this is to apply a force that's given by the desired acceleration. That's the first term that you see there, plus a term proportional to the velocity, a term proportional to the position error, and a term and then the gravity. That's all you need to worry about. So the problem is if I want to apply this control, the resulting vector might not be in the direction in which I can apply the thrust. So in the picture on the right, the thrust you can apply is obviously perpendicular to the plane of the vehicle, but the vector t is not perpendicular to that. So you do the next best thing. You project t along the direction in which you can apply the forces. So that's just a dot product, right? So it's going to get me roughly what I want to get, but not quite because the two vectors are not aligned. What's the next thing I can do? Well, I can rotate the platform so that the vector k points along t, so which means I have to essentially roll or pitch the vehicle so that those two vectors become aligned. And that's the second piece. We figured out what that orientation is, so we calculate the desired rotation, r desired, and then we calculate the error in rotation space. So this is, again, a little complicated. You have two rotations. How do you find the error between those two rotations? You have to do the computation correctly on SO3. But if you can do that, the rest of it is just, again, a proportional plus derivative control on SO3. So the only thing that complicates this is all the nonlinearities. If you know how to handle that, and if you're a control theorist, this is all pretty standard. So, and we know how to do that. And that gives you the total force you want to apply and the total moment you want to apply. And that translates directly into the rotor speeds that you want to apply. So all of this happens at 100, 200 times a second on board the vehicle, and that's the essence of control. The other thing we do, besides writing down these equations and implementing this in software, is get an understanding of what these terms are. So you'll notice one of the things that shows up here is I. This I is the inertia tensor, how heavy the system is and how distributed the mass is. So the more the distribution, the bigger the rotary inertia. And that comes into play in these equations. And it turns out that your ability to quickly stabilize degrades with the inertia. The bigger the inertia, the harder it is to stabilize the system. And this motivated us to build smaller vehicles. So this is work by Yash Mulgaonkar. This is 11 centimeter vehicle. From micro aerial vehicles, we've gone to nano, and now we're down to pico. So this consumes about 6.5 watts, max speed of 6 meters per second, which is about 3 times the brisk walk speed. But 6 meters a second normalized to 11 centimeters in terms of body lengths per second, that's pretty fast. That's like a 747 going at Mach 50 or something like that. So this thing could really zip for its size. Again, the small size, one of the added advantages is it becomes safer. So you can stick your finger in the blades and nothing happens to your fingers, which is important. When we first started working on this, one of the first things we had to order is a first aid kit. And now if I plot this histogram of Band-Aids consumed over the years, it's kind of tailed off with this guy. So you get safety with size, and of course the thing that we originally wanted, we wanted to make this maneuverable. And this is something you see in nature all the time. So I wanted to show you this video this is a really cool video of honeybees. You can find this on YouTube. Slowed down by a factor of 20, and you see these honeybees actually don't care about collision avoidance. This is the most basic thing in robotics. If you can't do obstacle detection and collision avoidance, you don't build robots. Well, nature clearly doesn't care about that. In fact, these things bang into each other. They probably learn from that, right? They learn because they contact the environment. So our goal is really at someday to be able to build really small UAVs so that we don't have to worry about collisions and don't worry about safety. So I want to show you some videos of what I think is the first planned mid-air collision, again slowed down by a factor of 20. And this is essentially using the same control algorithms I showed you. This is that Pico aerial vehicle, but now with a carbon fiber cage, which is designed so that the propellers don't entangle with each other. So this is a 2-gram cage, which is, again, very lightweight and, again, autonomously controlled to be resistant to collisions. So, again, only possible because of the small size and then the small inertia. So coming back to planning motions, as I told you before, we think about planning in the space and around obstacles. And someday we hope not to worry about the obstacles, but right now we do because our vehicles are a little bigger. And we plan these smooth trajectories. These trajectories are designed to minimize the fourth derivative of position, so we call them minimum snap trajectories. And again, this is a computational geometry problem. If you know what the obstacles are, you can sort of plan your trajectories around them. And once you do that, those trajectories get automatically mapped to this more complex space. And then I told you the control story, but this is the net amount of real-time software that has to run for control and planning on board. Of course, for this, I have to know where these obstacles are, and that comes later, but the control and planning is essentially this. And again, one of the things I want to emphasize is that we can't really decouple the mechanical design with the electrical design with the controls design. As you'll see from this video, this is Daniel Mellinger's work, and again, this is Yash Mulgankar's work. Bigger robot, smaller robot, again, the same degree of robustness. One of the things we can show you is that if you look at the basin of attraction, which is roughly speaking the envelope of conditions from which you can disturb the robot and have it recover safely, that basin of attraction grows inversely with L, actually L to the power 5/2. So it means the smaller you make the L, the bigger that basin of attraction, and the more violently you can disturb it. So this is sort of paradoxical, because you think about flying and you say, well, I want to be in the biggest aircraft possible. Actually, the smaller aircrafts are more robust if you think about recovering from really large perturbations. So that's one of the reasons we think about co-designing the mechanical platform and do the control system design. So if you take systems like this, and by the way, all of this is being done indoors in a motion capture camera environment where we get position feedback at 100 to 200 hertz, then the only real challenge is designing software for control and planning. And these are some of our minimum snap trajectories. If you know the environment and you place these obstacles, and the robot knows what the obstacles are, it can generate trajectories like this in a fraction of a second. And it doesn't matter if the the obstacles are moving. As long as it knows where the obstacles are, it can calculate these trajectories. So here again, the computation takes about roughly 1/40th of a second, and the vehicle sees the hoop, maybe 2 snapshots, extrapolates it as a function of time based on its knowledge of Newton's laws, and it's able to execute that. So in all of this, the only unknown thing is really the dynamics due to wind effects, due to near-ground effects, and those you have to learn over time. So we run a simple filter whose parameters we estimate over time. And there are a few other things you have to do maneuvers like this, which I'll tell you in a minute. So this is Justin Thomas's work and Kaushal Srinath, who's at Carnegie Mellon. So birds are able to coordinate flight with manipulation, and this is our attempt to do the same thing. This is a Philadelphia cheesesteak. But you could see, so that the challenge here, by the way, it's the same framework, but the challenge here is as the vehicle swings its arm back, you'll see because of angular momentum constraints, the vehicle actually pitches forward the other way. So that has to be planned. Again, there's a combination of model-based methods, but then some iterative learning, which allows you to essentially determine the correct parameters. So the first time we tried this, of course, it didn't work. But in 4 or 5 tries, you essentially get everything correct. And that's where the learning comes in. But there's a strong model-based component. And the same model-based component, this is Sarah Tang's work, and you'll see her trying to determine the exact trajectory that's required to carry this payload through a window that's a little shorter than the height of the payload. But again, if you have a model, then you can essentially fine-tune a few parameters to do this, and the learning again is based on a known structure. And then similar approach, this is collaborations with Mark Kutkowski's group with again Justin Thomas. So Mark Kutkowski's group at Stanford has pioneered these dry adhesive grasping tools, and now here we show how we can fine-tune the flight to arrive at this vertical surface with just the right velocities so that you have the right normal force, minimal tangential force, and you can just grab onto this. And actually releasing itself from the perched position is a little harder, and I don't have that experiment here, but it's something we've learned how to do, because when you release, it releases unevenly, and then you have to you have to recover from essentially a bad set of initial conditions. So this is something we've been working on with his group to allow vehicles to perch on different types of surfaces. So this gives you some idea of our approach to planning and control. And what I want to do next is talk a little bit about state estimation. Pretty much everything we did here relied on motion capture camera systems. So we did everything in the lab. These are our motion capture camera systems. The whole setup costs close to $250,000 with 16 4-megapixel cameras. And the way these cameras work is you determine positions of these reflective markers with sub-millimeter accuracy, and then you can determine the robot's position to within 2 degrees, within definitely less than a centimeter. So this is great for doing everything I've shown you, but if you go into buildings like this, you have to do this on board. Nobody's going to set up a camera system for you. And in fact, in this building, you can't even get Wi-Fi to work. So this is a big problem. So we've built a whole set of vehicles. This I'm showing you maybe a 4th prototype. This is a 2014 prototype, which essentially tries to do this on board. And the solution to this is to put cameras on board. You'll see a stereo pair. You'll see a GPS receiver for when GPS is available. There's a downward-facing camera, which you can't see, a pressure altimeter for measuring height, and of course an IMU. So with vehicles like this, you essentially try to use some variant of what is known in the robotics community as SLAM, simultaneous localization or mapping, or structure for motion, for those of you in the computer vision community. So I know you probably are all aware of this, but if you're not, let me just give you a very, very quick overview of this. So the fundamental idea is you have a robot, it doesn't know where it is. There's a whole bunch of features that are waiting to be detected. If it's a range sensor, it's probably reflections from features in the environment, like doors, pillars, walls, etc. If you have a camera, it's probably features that you detect in terms of changes in intensity, corners, and so on. But they're basically features, and depending on where you are, you see you see a subset of these features, possibly overlapping, could be disjoint. And you're also measuring how far you've gone as you go from one position to another. So there are these 2 sets of arrows, measurements that you make, and then there are these flows that you essentially estimate by integrating your IMU measurements. So you take steps and you have a rough estimate of how far you've moved. You take measurements, you have a rough estimate of how far these features are, where these features are. So you have a whole bunch of quantitative variables or you have a whole bunch of estimates that tell you something about the semantics of the edges. And then you have this big nonlinear optimization problem that you try to solve, and you want to do this in real time. And this is the essence of SLAM. So this is the first piece of the puzzle that tells us where things are in the environment and how we're moving relative to them. And then we have this architecture that needs to work 100 or 200 times a second. And this is our framework for estimation and control. And this is Xiaoji Shen's work. He's now a professor at HKUST in Hong Kong. And it relies around the use of a common filter, a variant thereof, a multi-sensor unscented common filter. So the idea is you get information from different sensors, a laser scanner, GPS, pressure altimeter, and they're all coming at different rates. And this sensor essentially integrates information from all of these, allowing for the nonlinearity in the dynamics and the sensor observations, and is able to provide best case estimates at 100 to 200 hertz, which bootstraps that controller I showed you earlier. Now, augmented with this is the SLAM software that I described to you earlier, and that essentially gets updated maybe every 20 seconds, every 20 times a second, sorry. And then the user interacts with this map. So the idea is that instead of specifying instructions in some absolute coordinate system, you now look at this map that's coming in, and you can point and click your way through this map. That's the best way to control a vehicle in an environment that you've never seen, and you're basing your instructions on the map that's coming to you in real time. And so that's the fundamental idea. And to show you the kinds of maps we can build, this is an example of work from Sikong Liu's his work. So this is just showing you how we can use onboard sensors to build maps indoors using a combination of laser scanners, Kinect RGBD cameras. And this is our lab. It's entering our lab on the bottom. This is, you can see with the clutter here, must be our lab. And you could see all this. So these are 5 centimeter resolution maps. You can see the trajectories, it estimates. So all of this stuff can be presented to someone who is not there, and that person can click his way or her way through this complicated scene. This particular trajectory was, of course, pre-programmed, but you could imagine this being done in an interactive fashion. So this is the indoor situation where we're able to use these sensors that are capable of dense mapping, like these RGBD sensors, and we're doing this in real time on board the robot. Outdoors, things become a little complicated, and I want to show you again Frank Shen's work. This is a combination of indoor and outdoor navigation. Again, the same idea. The user clicks on points, and the robot moves. What you see here is a combination of lasers, and this is the error ellipsoid that it calculates using the UKF. The ellipsoid is scaled up by a factor of 100, and the color tells you what sensor is being used. So for example, if it's this yellow color, it's GPS and vision. When it goes through the trees, for instance, you'll find that there was no GPS and only vision and laser worked. Between buildings, clearly GPS doesn't work because you're too close to the walls. And in a minute, you'll see it go indoors when it's dark, where only the laser works. And of course, in all of these, the altimeter works and the IMU works. But the key contribution here is we're able to integrate information from these different sensors and work in a variety of settings. The couple of things that we still don't know how to deal with is, one is, of course, smoke, and the other is if you're surrounded in a glass cage where everything is, I would argue even birds have a hard time flying with glass buildings and glass windows. But those are two things that are currently hard to do with this sensor suite. But again, you think about the challenges that Amazon is facing, for example, in terms of package delivery. Going from point A to point B in the sky at 400 feet above the ground, that's not challenging. The minute you come close to man-made features like buildings, or you come close to trees, bad things start happening. You can't really have a map for everything unless you cut down all trees and you prevent humans from entering an area. You say no cars in a particular area. And even then, you have to worry about the fact that near buildings you might not have GPS. And even then, you might have to worry about somebody who's trying to take this thing down with a baseball, right? So there are all these other things that we have to worry about, and this is our attempt to navigate close to physical structures in the presence of GPS and possibly in the absence of GPS, which eventually we have to solve for autonomous aerial vehicles. So lest you think that this is sort of solved, one of the things you'll notice is that we've actually gone in the opposite direction when we try to make these platforms smaller. So you think about this, I've put a laser scanner here, I put two cameras here, and these guys are pretty heavy. So this is 370 grams, that's an 80-gram module there. Batteries are a big problem, and you're consuming 200 watts per kilo of payload that you carry. So the bigger the laser scanner, the bigger your props need to be, the bigger the props need to be, the bigger the batteries need to be, and then, of course, bigger the motors. And so it's just scaling in the wrong direction. And you burn a lot of power. So we started asking, this is, by the way, 1,750 grams. So we started asking ourselves, is it possible to come up with a smaller platform, something which is inexpensive, something that's lightweight, something that has sensing, computing, and you can do all of this thing with a smaller package. So what is that? Well, obviously, each one of us has this, right? It's your phone. And that was the genesis of what we call the Flown, right? So you take an off-the-shelf vehicle. This is not off-the-shelf. This is ours. This is an off-the-shelf Samsung Galaxy smartphone. And this is in collaboration with Qualcomm. We use this Snapdragon processor and the suite that comes with it. And you find the lightest USB cable. This is a really short USB cable to plug into our vehicle. And everything that the robot does is actually done on a phone, including sensing the environment with the onboard camera in the back, which you take pictures with, which is actually a pretty nice high-resolution camera. And you'll see the same kind of minimum snap trajectories I showed you being executed on this phone, or the Flown, at 3 meters per second. So 3 meters per second is moving pretty quickly, and you can see the roll and pitch angles are quite significant. So this vehicle is not only able to do all this, but also estimate the ground effects. So the ground effects have to do with when you come close to the ground, you get a push off from the ground because of the downwash from the rotors. When you go close to a wall, you get sucked into a wall. When you go into the ceiling too, it's the opposite of the ground effect, so you get sucked into the ceiling. So something we found out the hard way, by the way. So, but the vehicle actually estimates all of this because it's doing visual odometry. It correlates what it sees, what forces or what rotor speeds it's commanding, and then it sees what motions it's achieving, and then backs off the ground wall effects and so on and compensates for that. So this is our approach to state estimation. We're trying to make this smaller. The one thing that the flown doesn't yet do is dense mapping. You can get the information, but to put all that information together in real time and build a dense map so that you can do collision avoidance and trajectory planning, this is still quite hard. Of course, there's a lot of interest from NVIDIA, Qualcomm, and so on to make this all happen in a package the size of our smartphone. So I think it's only a question of time, but right now we're not able to do it in this flown-like package. So let me move ahead and then talk a little bit about cooperative control, where like work that Dinesh and Ming are doing, we're trying to coordinate lots and lots of vehicles. So before I get into the details, let me just give you a high-level overview of one of the challenges, the mathematical challenges. And it's shown in this cartoon here. So let's imagine you're starting off with 3 robots at the positions S1, S2, S3, and you're asked to go to 3 goal positions. So I'm not telling you which goal position each robot needs to go to. So that's the first problem, right? Figuring out who goes where. So you need to actually number these goal positions G1, G2, G3. That's the first problem. This is obviously an assignment problem. It's a combinatorial problem, but you have to assign robots to goals, a task allocation or the assignment problem. The second problem is the trajectory planning problem. And remember, these are now continuous trajectories that you want to plan that respect the dynamics. I've already talked about this. You want to make sure that both of these things are happening simultaneously, and you want to make sure that these trajectories are safe, which means no 2 vehicles can come closer than 2 times r, where r is the radius of the vehicle, assuming it's spherical. And you want some sort of optimality. We'd like these to be very smooth trajectories, minimizing the snap and so on. And remember, you have to do both these problems. So the first problem, again, is a combinatorial problem. It scales as n factorial. The second problem is a challenge, motion planning challenge, and that scales exponentially with the increase in configuration space. So that's our challenge. So we can ask how to do this. Paradoxically, it's actually easier to solve the combined problem than the individual problems. And I'll talk about that in a minute. But if you were to essentially choose assignments that simplify this problem, then the combined problem, it turns out, can be solved in order m cubed. Actually, order m squared log m. M is the number of robots, but the trivial one is m cubed. So I'll come to that in a minute. But it's also useful to see how animals do it, how birds do it. So this is a picture of starlings off the coast of Denmark, 1 million starlings, and they do roughly the same thing. They form all these patterns, different birds going to different goal positions, although I'm sure they don't think of it this way. But they're solving this exponential or factorial problem. So we studied these. We've been looking at data from birds. We've also been looking at data from ants. So these are ants building bridges. These are ants carrying objects in collaboration with Stephen Pratt at Arizona State. So here what we do is this is a plastic object we create in our lab, cut from a laser cutter, and then we coat it with the juice from fig, and the animals think that this food. They carry it back to their nest. The interesting thing about this is if you can see which ants are actually pulling, which are pushing, and these guys are freeloaders. They're not doing anything. So you can actually study cooperation quite nicely. So we don't have a whole lot of insight to share from this, except that you can actually ask what architectures will respect these kinds of behaviors, right? So how can you build software that will allow you to do this variety of things? And this is quite obvious, but let me take some time to just go through this. So first thing is, in a team like this, there is no way you can coordinate the actions of all of these in a coordinated fashion. They have to act independently in order to be scalable. The second thing is you cannot have them require global information. By the time everybody gets global information, the task has already evolved, and you have out-of-date information, and you really cannot perform the task. The third thing is you really have to be agnostic to who your neighbors are. So the paradigm of anonymity, ants shouldn't care who their neighbors are. If I tell a group of you without knowing your names to carry this table out of the room, I bet you can do it, right? So it's that level of anonymity that we need to incorporate in our software architecture. So again, rather than tell you details about how we do this, I thought I would just give you 3 experiments that illustrate these things. So the first idea is this idea of leader-follower networks, which essentially means that robots pay attention to who their neighbors are. So in what I'm going to show you, each robot follows its neighbors and keeps track of the separation between its neighbors. So more precisely, it follows its neighbor's position, X, Y, and Z, and its yaw angle. And if it makes sure that that is acceptable, keeps to a desired value, or is within a certain range. And then some vehicles have global information, which is that they know where they are in the world and they know where they need to go. Now, in animals, that's never the case. No animal carries a GPS unit and says, I got to go to this location, right? But we have to be practical. We're engineers building systems, and we want to task them to go to particular locations to perform particular tasks. So you need at least one person who has some geo-registered coordinate system. You can have multiple people, but you need at least one. So the leader-follower networks idea is quite easy. So I just want to show you work that's about 3 years old by Katie Powers. And this appeared in Nova. David Pogue, who's the host of this, was essentially asked, so what if I were the leader? What if I were to do something with it? And we said, be our guest. And he literally hijacked one of the aerial vehicles, and he's moving it around. And the other vehicles that are communicating with it and trying to maintain relative position and bearing, they don't care that that vehicle is manually driven. So everything is done in an automated way. So he's able single-handedly to manipulate this small group simply by taking possession of the leader. So if you had multiple leaders, you would have a little bit of conflict between what he wanted to do, what the other leader wanted to do. But essentially, with a couple of leaders, you could essentially control a very large team. The second paradigm is this paradigm of anonymity, which is this notion of having robots that are unlabeled. This is Matt Turpin's PhD work. And again, this notional experiment just illustrates how you have a small team that's forming a circular pattern, and that pattern is formed on the fly with robots that don't know who their neighbors are. In fact, they don't even know how many robots are there in the team. And so they automatically move into formation or move out of it based on how many vehicles there are. So you can imagine for the same size circle, if there are many vehicles, they'll spread out. If there are fewer vehicles, they'll try to cluster in. And that happens naturally in this framework. So once you have that, you can think about how to achieve these very large shapes and how to move them around. And again, this is Matt's work. They start off from a circular formation, and then you'll see them deform to this elliptical formation, stretch out into a straight line, back into a circle. And all of these formations are being specified at the level of equations. So you specify 3-dimensional curves, and the vehicles will fall into those curves. And if those curves are time parameterized and they change, then the vehicles essentially follow that. So, so these are some of the things that we can do using our methodology. And what I'd like to do next, though, is tell you a little bit about some of the applications we're doing. So why do all of this besides making cool videos? Well, we want to solve some really meaningful problems. So If you can control individual vehicles, if you can control them to coordinate with each other, then there are quite a few things you can do with aerial vehicles. So I have 5 minutes left, so let me just tell you about 3 applications we're pursuing. So first is what I call the Amazon prime air problem, and this is, again, Sarah Tang's work. What we're trying to do is, again, imagine that all of us have ordered packages, gifts for Christmas, and so imagine in Raleigh, around the December 23rd framework, there are probably hundreds of vehicles in the sky all delivering packages. So how do you essentially get them to navigate safely to their destination? And how can you guarantee that no vehicle will run out of battery while it's in the air, right? So this is the idea. So they're starting off at different locations, all marked S, and they want to go to these goal locations. And you'll see what happens is, as they head towards their goal location, so this one, for example, is heading there, this one is heading there, this green one is heading over here. As they head off to their goal locations, they encounter each other, and they spontaneously form this circular holding pattern, much like you see in air traffic control. And you have to remember now, they're all flying, well, 400 feet is the limit, right? That's what the FAA has specified. So they're probably flying at 395 feet, right, just below that horizon. So it's a 2D problem. It's not really a 3D problem, because they don't want to get any closer to the ground than they have to. So if you can solve the 2D problem, the 3D problem is actually simpler. So that's the idea. And you will see that the same thing, if these problems are decoupled, there are 2 different holding patterns that are formed spontaneously. In some cases, no holding patterns, and just one with 15 vehicles. And this just shows you some of the work that, some of the simulations that illustrate the algorithm at work. You will see that some of these are slowed down, but we have suboptimality bounds that tell you how bad the performance can be. And if you know what those bounds are, then you can size the mission with the right batteries so that no vehicle runs out of batteries. So this you have to do up front. But basically, we're asking, what would it take to deploy 50 vehicles within 2 city blocks? This is sort of the worst-case scenario. If you think about 2 city blocks in Philadelphia, we can't imagine there'd be more than 50 residents ordering packages at the same time. And so that's the scenario we're looking at. So this is one of the applications. The second thing we're trying to do is look at how we might use vehicles like this in precision agriculture. One of our robots, the one actually I showed you in an apple orchard, and these robots have the ability now to navigate apple orchards like the ones you see here. You will see that they're able to go between the rows of crops. They're able to gather images from the air, which this is infrared imagery. This is 3D map information, much like I showed you navigating indoors. This is the same thing, but you're able to measure the size of every tree, how big the canopy is, where the fruits are, and then monitor that as a function of time. And this is the measurement of an index called the NDVI. Again, these 2 are taken from the air, and NDVI tells you something about the vigor of each plant. So just like in personalized medicine, every person is treated differently. Here we're thinking about how to treat every plant differently. And again, you have multiple vehicles do this because you want to cover large areas in a very short amount of time. So we think approaches like this can really increase the yield of fruits in orchards like this. More importantly, it'll decrease water consumption. Agriculture uses 80% of today's water. So if water is a problem, you first have to tackle the agriculture problem. And that's what we're trying to work on. The second thing we're doing is trying to realize this vision of a robot first responder, and this is Karthik Mohta's work. So vehicles like this can one day respond to your 911 calls, or if there's a terrorist attack or something like that. So here you see a flock of vehicles all heading to a building where there's there's an emergency call, and this is showing you what a dispatcher might see. So we're trying to persuade Penn police to deploy a system like this. So there's the building, and you see these. By the time Penn police can get here, it's probably going to take 5-10 minutes, but our vehicles can get there right away. They surround this. Very, very preliminary result where you could show from these very inexpensive cameras with over Wi-Fi. They're quickly constructing a map of the region. This is real time. This is 1/3 real time right now, but we can also make this 3-dimensional. So the idea is before first responders come on the scene, they already have that information, and that information, if you followed the O.J. Simpson trial, if there's a white Ford Bronco, we know it's there, and we can tail it before the police get on the scene. Maybe you're too young for this to remember that story. But that's the idea. So just quick situational awareness. And not just outdoors, we can also do things indoors. So this is some experiments we did with Satoshi Todokoro's group at Tohoku University. You see our vehicle traveling with his ground robot. And again, the reason we wanted our robot hitches a ride is because it's always short of energy. So it's programmed to be lazy. So whenever possible, it hitches a ride. But you could see in front of this collapsed doorway, when it gets stuck, the ground robot releases the aerial robot, and it's able to go through this. This is sped up by a factor of 2, and it's creating these maps. Let me skip through this and instead show you the kinds of maps we can build. So this is a map we built of the electrical engineering building at Tohoku University shortly after the March 2011 earthquake. Collapsed building, 3 floors, and these were essentially to build maps to verify structural integrity. There were no victims here. This happened 2 months after the earthquake. But we were able to develop these maps and get reasonably high resolution maps without human intervention. Of course, this took 2.5 hours, so it's not really a practical tool. No first responder is going to give you 2.5 hours to let your robots do their thing, right? They'll probably give you 2.5 minutes if you're lucky, maybe 2.5 seconds. So that's where this notion of swarms comes in. We really want the vehicles to go and fly in, collect all this information, and think about efficient ways of integrating this information. I've seen a lot of work that's being done here on 3D reconstruction, and we should be able to do this from robots that are not particularly well localized, but have some information about where they are, where they took the pictures from, and then could you build a 3D reconstruction in a fraction of the time using cloud computing, parallel architectures, and all kinds of fancy computational tools. So that's really all I wanted to say. I just wanted to point out there are a few things in this field that we should really be thinking about. First, I think it's really easy to get into this field because of the democratization of science and technology. So this is a great opportunity for us, but it's also a threat because obviously people can do bad things with it. There's a problem with asymmetric threats. So I can develop a swarm for doing useful things. It's also possible to develop swarms for doing bad things. In fact, it's much easier to develop swarms to do bad things. So Leslie Kebling used to say it's very easy to write bad programs, and that's true. It's very hard to write good programs, provably safe. I think safety is a big issue. The FAA is sort of worried about this. Cybersecurity, we think about hacking into networks, hacking into swarms of machines. I mean, that's an order of magnitude worse. And then there are issues of privacy, but I really put this at the bottom of my list. You know, do we really care about privacy because of drones when all of us probably have pictures, embarrassing pictures of us on the internet that we don't know about, right? So I think, yes, privacy is important, but that, for me personally, is the least of my concerns. So let me just conclude with a poster of a movie that's going to appear soon called The Swarm. This is actually an old movie. Have you seen this? Any science fiction aficionados here? Have you seen this movie? Then you know this is a terrible movie, not to recommend it to anybody. But I love this poster. Everything about this poster is true. Size is immeasurable. The power is limitless. Even this piece is true. Its enemy is us because we know how to deploy this technology. The question is how to think about the business innovation that actually makes this practical for applications that are meaningful and will have a socioeconomic impact. Well, thank you very much. This has been a great pleasure. I'm happy to take questions.
Because the network is going to go down at 5 o'clock, so we are going to ask the remote side if they have any question. First, Duke. NC State. Any questions?
They probably left.
They're trying to ask questions. Can hear them. David, are they on? Okay, we hear something. Can we turn the volume up? Can you go to the mic? Yeah, that's them. That's Duke and that's NC State.
No questions from NC State.
Nope. Nope.
No question for NC State. Folks at Duke?
Question from Duke.
Okay, please.
How do you deal with the rolling shutter on the phone?
This is a global shutter camera. So, in fact, this is your standard camera. So it's not, I'm sorry, it's a rolling shutter, standard rolling shutter camera. So all the problems that you get with a cell phone camera, you're stuck with those cameras, those problems. So for example, in poor light, we don't do too well. You'll notice that we try not to yaw rapidly. If you do, then feature tracking becomes a bigger problem and it's hard to do visual odometry.
Does that answer the question, Duke?
Thank you.
It's probably
Okay,
a bad
great.
answer.
Any other question from Duke? Any additional question from Duke? No? Okay, great. Okay, so here, audience at UNC. Henry, go ahead.
So there are all these great things, Vijay, that you've already done. What are the things that you dream of doing in the next few years that you cannot do now?
Smaller, faster, smarter. Actually, I have 5 S's: small, smart, speed, swarms. I got one more S. I've forgotten what it is, but no. Seriously, seriously. Well, so I think if you think about it, everything should be. There's this convergence between smartphones and robots, and really, this is this factor you want to deal with. If you have a size like this, then you can really think about flying through buildings and collecting information in real time. So what is preventing us? Well, it's a combination of being able to integrate sensing, perception, planning, and control. That's one challenge. The second challenge is communication, computation, reconstruction. And I think the third challenge is knowing where to go and who should go where in a setting where not everybody has the same information. So it's what I loosely call information gathering. So those are sort of the 3 challenges, but they're all driven by these S words. Yes?
Can you say something about the state of the art in the drones themselves? What's their typical range? And I suppose maneuverability is some kind of a trade-off between battery power and motor power and motor side, all that kind of stuff.
So the one fact is that these drones will consume 200 watts per kilo. So 200 watts is a lot. If those of you who go to the gym and exercise in the elliptical or whatever, you probably consume about 2 watts per kilo. So these consume 10 times what you consume. An interesting fact about cell phone batteries is that these batteries will lift a human being 6 floors. So if you take the total amount of energy that's consumed here, that's roughly, we'll take a 100-kilo person and lift them about 6 floors, right? This is what we have, and what we want to do is to drain this at roughly 200 watts per kilo. So the only way you can extend your life for small vehicles of the size I'm building is by making them lightweight. Hence the size issue, the weight issue. If you look at commercial drones, they don't care about size because they're navigating outdoors. Very few of them, in fact, I don't know of any one of them who thinks about a business case for navigating indoors. When you navigate outdoors, you can make things bigger. When you make things bigger, this problem scales the right way. And you can put big batteries on it. So it's not uncommon to see off-the-shelf platforms can travel half an hour. Well, in half an hour, if you can travel at 20 meters per second, which is a lot, by the way, you can do a rough calculation of how far you can go and come back. Unlike an airplane, which burns fuel and gets more and more efficient as time goes on, here you're carrying dead weight as you burn off the battery. So things don't scale quite the same way as they do for airplanes. But the summary is if you're able to build things, make things bigger, then you don't have to worry about a lot of the challenges that we worry about. But you do have to worry about safety. You do have to worry about maneuverability. People really don't care about maneuverability. If you're up in the sky, I mean, if you're piloting a 747, do you really care that you can't do 2.5 somersaults in the air? No. But for small ones, you want to have that maneuverability. Did I answer the question?
I think so. I was just wondering, in your applications, you didn't talk about a couple of things that are sort of obvious to me, and that's the use of drones in dangerous places like, well, you talked about disasters, but I'm thinking like bomb squads and radiation
Yes.
leaks and so forth.
Yeah, so this is a problem. This is how I got interested in the Fukushima problem. I'm still interested in that. The fact is we still don't know what's inside that reactor building. And someday we want to be able to fly inside and be able to look inside. So we're working in TEPCO on this very issue. This is definitely, by extension, one of the challenges, but we have nothing to show for it. Yeah.
So we all think there's a lot of prediction about drones exploding. People think 5 years from now, 10 years from now, we all have a personal drone. So imagine Earth being with 1 billion drones. Now, there could be Amazon drone, there could be Microsoft drone, there could be Google drone. It's not a cooperative world anymore.
Yes.
And we see that in traffic. We see
Yes.
that in humans.
Yeah.
You know, as they explode, can't like 1 billion people collaborate.
Yeah.
How would that situation, the asymmetry, because right now you design 10 drones in the building, you go left, you go right.
Yeah.
But like traffic, right? Or like you go to traffic in Asia, we talk about Indian traffic. Right?
Yeah.
Everybody driving in every direction.
Yeah.
What do you expect to happen?
So you can do the equivalent of what Apple does with iTunes, digital rights management, and try to, which is what I think the FAA is thinking about. So let's say all the drones are registered. And by registering, they essentially agree to communicate. And there's the equivalent of a transponder that you can't turn off. That's an answer to the problem. But you and I know it's hard to legislate these things. And we build our own. I mean, who's going to you can't just say you're not allowed to build when things become so easy. So I think it's a great question. I do think that one of the challenges, in going back to Henry's question, is really being able to detect other vehicles. So for a Google car to detect another car, whether it's driven by you or me or another Google car, is not that hard. But for these little guys to detect other little guys is a huge problem. And I think that's where we need an order of magnitude improvement in sensing to enable that. So you're outdoors. You see something coming at you at 10 meters per second. I'm going at 10 meters per second. Well, at 20 meters per second, if I can accelerate, if I can slam on the brakes at 2 Gs, I still have 40 meters to work with. So I have to detect something 40 meters away and be able to slam on the brakes. And that's the problem if everybody has a drone. And that goes back to the safety question that I talked to you about. But it's inevitable, so it's something we have to deal with.
A little bit harder than traffic we have to.
I think so. I mean, one of the benefits of traffic is you have a crash and you're right there. These things crash, they come down on you. So there's this minor problem with gravity that, yeah. So no, I really think this is a big issue. So that's why I said it's good that the barrier to entry is low, and it's also bad because now everybody will. I think these companies are selling drones for whatever $1,000, $2,000. I mean, engineers are just going to start building them themselves. This is going to be like this old. We used to build our own radios. If you're an electronics fan, I remember my first radio that I built. It was so easy to build. I think this is going the same way. Yes.
I'm following your research for the past 2 years, and I'm completely familiar with your work. In ETH University, they are using the SOAR to build the walkable rope bridge. So, to best my understanding, the SOAR that you make is better and computationally inexpensive than theirs. So I want to know that in the future, do you want to go and construct something with the soft material like a rope, or you rather to just stay with the, some hard components like the construction with the, metal?
It's interesting to ask if so the logical thing in construction is to think about what you can do top down as opposed to bottom up, which is how buildings are built now. So you think that aerial robots have a huge potential there. And while we've done some work there, the problem comes when you try to scale things up. Again, it's the 200 watts per kilo. If you have to carry big things, you have to have big vehicles. And then it's not clear to me that there are real advantages of this, because it's much easier for me to build cranes, and which is how things are done now. So I think there's a question of economics. There's another question you asked about building materials, and this has more to do with building architecture and so on. And you can argue that how we build buildings today is old-fashioned, and we should be thinking of novel materials. But I'm not an architect. I know many architects will agree with you on this front. So the rope bridge thing, I think, is similar to the kinds of things we've been doing. It's more an exploration of what is possible with aerial vehicles. Can you do complicated things with aerial vehicles the same way you can do with ground vehicles? And Raf D'Andrea is obviously one of the top people in this area. His lab does a few things. My lab does a few things. So I'm not sure that either of our labs is addressing the real problem of how to do construction. People are questioned out.
Any other question? Okay. No more questions? Okay, great.
Thank you.
Thank you, Chair. All right, and we have refreshment outside, so help yourself.
I think you can just turn on.
I just want to.
Let me just turn